Hello everyone. In order to introduce the topic of this video, I'm first going to talk about Pascal's triangle. As a quick reminder, this is how you construct the triangle. You first put a 1, and then to get the next row, you add every pair of adjacent numbers and write the result under the two numbers. You can keep doing this to get as many lines as you want. You can see why it's called a triangle. The numbers of the triangle are called the binomial coefficients, and they show up everywhere in math because they have a lot of properties. You can also build the triangle from the bottom up. To do that, you just subtract the terms two at a time. Now we can do something interesting. What if we try to build the triangle from the bottom up, but we keep going after we reach the initial 1? You can just imagine that every empty space is a 0. This is what we get. Okay, so we have a lot to discuss here. First off, I didn't write the entire lines because they actually go on forever to the right. We can also see negative numbers on every other column. And if I add more lines, we can see that the original Pascal's triangle appears, but with some minus signs and it is tilted. Since we've extended the triangle, it will be interesting to see if the properties of the normal triangle remain true for the new lines. One property in particular is very interesting. If we add all the terms of one line of the triangle, we get 2 to the power of the label of that line, if we say that the initial 1 is a line number 0. You can easily see why this is true. Every line contains 2 copies of the previous line, so the sum doubles with each line. So, if this property is still valid for the new lines, this would mean that this infinite sum converges to 1/2, 1/4, etc. But this is obviously wrong. How could a sum of integers add up to a fraction? It makes no sense. And yet, I'm sure some of you have seen things like this in the past. Namely, this 1 minus 1 plus 1, etc. equal 1/2. The question is, how can we rigorously give a meaning to this? The usual way of adding up multiple terms is called summation. But what we actually need is a new type of sum, the supersum. The usual summation is like a transformation that takes a sequence as an input and outputs the limit of the sum of the terms of this sequence. But obviously, this will only work if the sum converges. A supersummation is also a transformation, but it also allows sequences which some don't converge. But other than that, it is very similar to the usual summation, because a supersummation must have 3 properties: linearity, stability, and regularity. The linearity has 2 parts. First, you will get the same result if you first add up 2 sequences and then take the supersum, or if you take their individual supersums and then add them up, just like the usual sum. Secondly, the supersum of a sequence multiplied by a coefficient is equal to the supersum times the coefficient. Again, we find this property with regular sums. You can either factor out the coefficient, or you can distribute it to all terms. For the stability, we first have to introduce a new transformation E that is very simple. It adds a 0 in front of all the terms of sequence. This stability tells us that the supersum doesn't change if you add a 0 to the sequence. This time, it is very obvious that it is also true for regular sums. Anything plus 0 is still the same thing. Lastly, the regularity says that if the sum of the sequence converges, then the supersum has to be the same value as the regular sum. This makes sure that our supersummation is consistent with the real limit of the sum. And there we have it, the 3 core properties of the supersummation. As I've mentioned before, the main point of the supersummation is to be able to give a value to a sum that doesn't converge. All sequences can't be supersummed, but at least we have more sequences. And you might have guessed it, the new lines of our triangle corresponds to sequences that have a supersum. First, we'll do some simple examples so you can see how it works. Let's take this geometric sequence and let's try to find its supersum. The goal is to use the function e from the stability property. We can notice that the nth term of e of u is the n-1th term of u. So you might think that we can rewrite the recurrence formula like this. Well, not exactly. If we write them next to each other, we indeed notice that they are equal after the first term, but the first term doesn't match. To fix this, I will introduce a correction sequence epsilon, which is equal to 1 everywhere except for the first term, where it is equal to 1. Now, if we add this correction, we can write this new relationship here. It's time to take the supersum on both sides. Now we will have to use our three properties to find the result. First, we use the linearity to split the sum and then take the 2 out of the t. Then we use the stability to get rid of the e. And now we use the regularity to find the actual value of this t of epsilon. It is clear that the sum of the terms of epsilon converges. 1 plus 0 plus 0 etc. is equal to 1. It means that t of epsilon has to be equal to 1 as well. And there we have it, the supersum of the powers of 2 is equal to -1. You might have seen this equality in the past, and what we just did is the same thing but more rigorous. And by the way, we can easily do this in the general case for the powers of q. In the end, we find this formula for the supersum of a geometric sequence, which corresponds to what we already know when the sum converges. We also notice that q can't be 1 because of the denominator, which means that 1 plus 1 plus 1 etc. can't have a supersum. And for those who are curious, we can have a supersum for 1 plus 2 plus 3 etc. with this supersummation, because of a similar problem. Hope you're not disappointed, you won't see -112 in this video. We can also find the supersum of the Fibonacci sequence. We will once again start with the recurrence formula and write an equality like this. We now need to find the correction sequence. We can easily do it by comparing u with the sum of e of u and e of u. We can now once again simplify the expression. T of epsilon is 1 plus 1 equals 2. And so we get that the supersum of the Fibonacci numbers is -2. Now we can get back to the triangle. The first new line is this one, and it is actually the powers of -1. Using the formula we found earlier, we can conclude that this supersum is indeed 1/2. Now, here's the second new line above the first one, and I'll draw it a second time like this. Because of how the triangle is built, the sum of two consecutive terms of the second line is equal to the corresponding term of the first line. And if I move the box here, it still works. If the first line is m1 and the second line is m2, then this is e of m2. And I've just showed you that m2 plus e of m2 equals m1. We can now compare the supersum, and after getting rid of that e, we can see that the supersum of f2 is half the supersum of m1, which means it is 1/4. And you can do this for every other new line, which explains why we get the negative powers of 2 for the new negative lines. So this is it. This is how you can make sense of those infinite sums that should be equal to a number, even though they don't. The property of the powers of 2 can still be true in the new triangle, but we have to talk about supersums and not simply sums. In general, it turns out that every sequence of that form, or almost all of them, have a supersum. We say these sequences satisfy a linear recurrence. We can, as we did with the examples, use a correction sequence to get the e of u's, and then simplifying it and factor t of u. We can calculate t of epsilon in the general case. I won't go into the details, but in the end we get this awful formula. It is very tedious to do, but we can prove that this formula will respect all three properties for all such sequences. Before the video ends, I'd like to share with you one use of supersummation. We can use them to figure out general formulas for the value of these sums. The general term is like a geometric sequence but multiplied by some power of k. This kind of sequence actually satisfies a linear recurrence. In this situation, the first term and the coefficients of the recurrence formula are very specific, and we can use the previous formula to get this new monster formula for the value of the supersum. It means that when the sum actually converges, which occurs when q is between -1 and 1, this formula will give us the real value of the limit of the sum for any power of k. So, for every value of the exponent, we can evaluate this big formula to get another formula for this precise exponent. Here are the first few ones.